system in Scala 3. So I'll give an example use case for that. So in Scala 2 right now, say you are a library author and you want to give your library users the opportunity to automatically derive type class instances for your library's type classes. There are a few different choices. Probably the most sensible option would be Magnolia. Traditionally, it's been shapeless, but then John Pretty came along and built Magnolia, which is it's focused on fast compile times, and it's quite a nice, simple API that you can use just for type class derivation. Shapeless is still great for a lot of other things, but just specifically for type class derivation, Magnolia is probably the way to go. There's also the option of not using either of those and hand rolling it from scratch using macros, which I have done and I wouldn't recommend. In terms of how users can actually make use of this feature, how can they opt into generic derivation of type class instances? There's a few different patterns that have kind of evolved organically over the years. The simplest is to define or to implement generic derivation in the type class's companion object. And that means that users don't need to opt into it. It's just turned on automatically. But it also means that they can't opt out of it, or it's very difficult to opt out of it. So this is not really recommended these days because it can lead to huge compile times and quite surprising magical behavior if the user's not aware that this is happening. As alternatives to that, libraries like Circe have come up with a choice of imports. So you can import generic auto underscore to say, I'm happy with generic derivation everywhere. I don't want to write any instances myself, just do it all for me. Or you can import generic semi-auto underscore to give yourself a bit more control and say, I want you to automatically derive an instance for this particular type that I've chosen. So there's a few different patterns, but it would be nice if the language provided one way to do this, and we could all agree that this is the right way to do it. So that's what Scala 3 is trying to do. Just to give a bit of context, we can have a look at how Haskell does this. Haskell has been doing generic type class derivation for years now. It's way ahead of us in terms of maturity. And it's all based around this keyword deriving that you can put onto your data types. By default, out of the box, GHC can derive a few stock instances. It can derive things like equals and show some very simple type classes. But then there's all these different language extensions that have appeared over the years to derive more interesting things like Functor and generic. Recently, I think the most recently added extension was deriving via, which is very powerful. It means that you can reuse existing instances in order to define instances for new types automatically. So you can avoid writing some very boring code. So we can have a quick look at how this actually looks in Haskell. Here I have some example code. We've got a data type here, user. This is a sum type, so a user is either a logged in user or they are anonymous. And we can see that there's this deriving keyword, and we're asking GHC to automatically derive show and equals for this data type. And these will be derived just as you would expect. We don't need any language extensions for this, it just works out of the box. Down here we have a higher kinded data type. We've got the data foo, which takes a type parameter a. It's got one constructor, it's two fields, a field of type A and a field of type string. because it's got this type parameter a, that means that we can derive functor for it. So we can map over a foo type. In order to make this work, you can see on the very first line of the file, we've got a language extension derive functor. So we've opted into this. Then we have an example of mapping over a foo. So we create an instance of foo with field values 42 and hello. So this is a foo integer. And then we map over it using this fancy map operator that they have in Haskell. We pass in the function which adds 1 to it. So we map over the foo with a function that adds 1. So we would end up with a foo 43 hello. And finally, an example of deriving via. So here we have a new type called price. So a new type is a zero-cost wrapper around an existing type. It's useful if you are into domain modeling and you, rather than passing integers and strings around, you want properly named types. So you can't accidentally mix up a user ID with a booked ID or whatever. They would be separate types. So we have a new type of price, which wraps integer, and we can derive semigroup for it because we already know how to sum integers. There's already an instance available for sum semigroup that adds integers together. So we can use this deriving via system to say, do the same thing as that, but do it for my type, because my type is very similar to int. So there's just some examples of this in action. I won't bother running this code, but you can guess what it would do. Okay, Rust is clearly quite heavily inspired by Haskell. It also provides quite a similar feature for type class derivation. Instead of a deriving keyword, they went with a derive attribute. So this hash square brackets thing in Rust is called an attribute, and you can attach it to your various structures in your code. So say you have a struct in Rust, which is a bit like a case class in Scala. You can stick this derive attribute onto it and say, I want to derive these instances for this struct. Again, just like Haskell, it can automatically derive a few stock traits like equals. And if you want to derive your own custom traits, then you can provide a macro to do that. So as a library author, say you provide your own trait, which is like a type class in Scala, and you want users to be able to automatically derive instances of that trait, you can provide a macro as part of your library to do that. So we can have a look at how that looks in Rust. Here we have a struct person with 2 fields, name and height, string and integer. And it's got this derive attribute on it. It's deriving debug, partial equals, and equals. Those 3 are stock traits that are available out of the box. And then this implement height one here, this is not the name of a trait, this is the name of a macro that we've provided as part of our library. And that's going to derive an instance of this trait height that we have down here. So given a person's height, which we assume to be in centimeters, it's going to provide an implementation of height instance. So it'll fulfill the requirements for this height trait. We can have a look at how the macro looks. So on the left-hand side, we've got our library code. This is the macro code. And it's got this special attribute here called proc macro derive. and we've got the name here, implement height. So this is the name that we're kind of registering our macro with, and that matches the name over on the right-hand side, implement height. Then the actual macro function itself, you can call it whatever you like, that doesn't matter. As input, it takes this thing called a token stream, which is as bad as it sounds. This is just a raw stream of lexical tokens. So there's no AST, there's no type information here. You take in a stream of Rust lexical tokens, and you have to return a new stream as your output. Luckily, somebody in the Rust community has done the hard work and produced this library called Syn, which takes care of parsing that stream. Sorry, loud motorbike outside. Takes care of parsing that stream and turning it into an AST. Still, there's no type information, but at least you have access to the syntax tree. So the first step that we do is to parse the stream into an AST. Then we can extract the name of the struct from it. And then the result of the macro, what we return, we just write it as a string. So this is a very silly example, but here we're providing an implementation of the height trait for whatever the name of the struct is, and we're providing the height in meters implementation here. Okay, so that was Haskell and Rust, a whirlwind tour. You can see that they were both doing quite similar things, where the user of your library will add some kind of deriving keyword or derives attribute onto their own data types to say they want to derive instances of your type class for their data type. And Scala 3 provides a very similar mechanism. So there's this new keyword, derives, which you can add onto your ADTs and enums. So we'll have a look at that. And there's also this new feature called a mirror, which can be used to derive these instances without having to reach for the awesome and terrifying power of macros, unless you really need to. So for the vast majority of type classes, a mirror is all you need, and in theory, it's simpler than using macros. It provides just enough features to implement type class instances and nothing else. So let's see those in action. Let's live code some Dotty. What could go wrong? So I've written some data types here. We've got a data class person with a name and a height, familiar from Rust. We've also got a pet, which has a name and a species, and an owner, which is a person. So we have a nested case class situation here. We've got a case class whose field is another case class. And then down at the bottom, we've got an enum. So this is our first new Dotty feature, enum. And this is just a much nicer way of writing sum types than the way that we have to do it in Scala 2 with sealed traits and case classes and case objects. So in Scala 2, this would be sealed trait employee, and then case class grunt extends employee, and case object CEO extends employee. So there's a lot of noise there. Here we just have the essence of what we're trying to do. We've got an enum with a couple of cases. And this one is actually a recursive ADT because grunt can have a boss, which is another employee. So we've got an ADT that refers to its own type. So with these three types here, we've kind of covered the most of the interesting corner cases of ADTs that we'd want to be able to handle when we're deriving instances. So let's try to write show and then derive some instances for it. Now, how do we write a type class in Scala 3? It's quite similar to Scala 2. It's just a trait. Oh, it's even going to autocomplete for me. I'm going to call it a show. It'll take one type parameter A, and we'll have a show method which takes an A, returns a string. So given an instance of A, some value of type A, we're going to turn it into a string so you can pretty print it. Now this is how we would write it in Scala 2. So say you had class foo, then you would do like implicitly show foo dot show, and then you pass in your instance of foo. This is how it would work in Scala 2, but in Scala 3 we can make this a little bit more ergonomic because we have a new feature called extension methods. So if we switch this around a little bit and add a dot, we can write this as an extension method. That means given any value A of type A, it will now have this new method on it called show, as long as it's an instance of the show type class available. So instead of this, we would just write foo.show. So the entities have switched order and it all looks a bit nicer and more object-oriented and a bit more natural to write. So we'll go with the extension method approach. Now we have a type class. Let's see what happens if we try to add a derived. My library.show. Is that in the right place? I can't remember. Enum has it derived in one place and case classes have it in another place. I think that's the right way around. So
I don't know if metals would work with dotty, does it?
It kind of half works. Let's try compiling and see what happens. Okay, that's good. This is what I expected to happen. So we get an error saying value derived is not a member of no type. This shouldn't say no type. This is a bug in dot. But it's looking for a method in show called derived, which doesn't exist because we haven't written it. So that kind of gives a hint about what this derives keyword is actually doing. When you write derives mylibrary.show here, this is actually some quite basic syntactic sugar for what it does is it adds a companion object person if one doesn't exist already. And in there, it adds even, which in Scala 2 would be like an implicit val. Even show of person. It calls this derived method with type person. So this in Scala 2 would be like implicit val show person, show of person equals show dot person. So there's just a convention, very simple convention that in your type class's companion object, so show's companion object, you as the library author have to provide a method which is called derived, takes one type parameter, and returns a type class instance. So I'll get rid of this because the compiler was writing it for me. I'll add things onto here and here as well. So let's have a go at writing this derived method and see what happens. It needs to take a type parameter A. Well, it doesn't have to be called A, but we'll call it A. It's going to return a show of A. So show of A. And it needs to implement this method. We'll just put a placeholder for now. So if we try compiling again, oops. Okay, it now compiles. And if we look at the main method, I've already made some test data. We've got a person, a pet, and an employee. We'll make this, we'll help a method called showMe. So for any type A which has a show instance available, given a type, an instance of A, it will return you a string by calling the show extension method. So if we uncomment these and run this thing, we get to do 3 times, which is what we expect. So here we can see that it's calling our derived method.
Chris, I'm not sure if we can see where you're running it.
Oh, really?
That is to say, can't see your terminal. You can see the code.
Let's switch to my terminal now. You can't see that?
I can't.
Can anybody
Not
see
sure
that?
if anybody. Can anybody see?
Oh,
okay, maybe it's just me. Okay,
Okay.
all right. That's absolutely fine then.
The majority can see it. We have quorum. It's a bit noisy. Do you mean the sound is noisy, or there's like artifacts in the video?
I think either way, there's probably not much we can do about that.
No. Okay, I'm just going to carry on. Hopefully, people can see. Right. So how do we go from this placeholder derived that doesn't do much to an actual derived method? I'm going to have to speed up a bit, so I'll get rid of this. And here is one I prepared earlier. Imports. So I'm going to gradually uncomment this and explain it as I go along. But here is the entry point, the derived method. It's become inline, don't worry too much about that. But it's now using one of these mirrors that I was talking about. So using is the same as an implicit parameter in Scala 2. So just imagine this as implicit. So given that you have access to a mirror of this type A, or person in our case, I'll provide you a show of person. To do that, we do a match on the mirror, and we just have a look at whether it's a product mirror or a sum mirror, and we handle each case separately. So ADTs in Scala can either be a product type or a sum type. A product type is like a case class, and a sum type is like an enum or a sealed trait hierarchy. A product is made up of a few different fields, and a sum is a choice of different types, also called a co-product sometimes. And let's have a look at the product one first. So this is going to be a case class, for example. This would match our person case. So say we have a case, an instance of a person. We have a name and a height, I think. What would we want person.show to actually produce? I would say something like, we want the name of the type of, the name of the case class as part of our show string. And then we'd want basically what I have above. So we'd want a comma separated list of the fields. So let's have the field names as well. That's quite useful. So I have like name equals this and equals this. So this is what we're aiming for. So in order to produce this or construct this string, we need to get hold of a few different bits of information. We need the name of the class, we need the names of the fields, and we need the values of the fields turned into nice strings. So we want to recursively call show on each of these fields so that we can get a nice, pretty printed version of the field value. Let's start with the name person, or the class name, which I've called product name here. So we're going to make use of this thing that the mirror provides, which is called mirrored label. But if you'll notice, this is not a value, it's not a string, it's a type. So this is actually going to be the singleton type of the string person. So if you were to write it out, it would be like, I don't know if this is valid, if you can actually write this, but this is the kind of idea. It's the singleton type of this string here. Singleton types are available as a real feature in Scala 3. So the way that we extract the actual value, the string out of this, is using this handy method called const value. The const value of this type returns us the string with that type, which is person. So that's exactly what we want. Next, we want the field names, which are name and height. And we make use of this thing called mirrored LM labels. Again, this is a type rather than a list or anything like that. And the type of this is actually a tuple type. It's kind of a tuple of singleton string types. So it's going to be like name.type and height.type. So we need to somehow grab the strings out of this tuple. I've made a little helper method called lm labels to do that, which is here. So this is where things get pretty weird. We take some type t, which is a tuple. We're going to return a list of strings. And we're going to do that by matching on an erased value of type t. So that means that in our cases here, this has to be underscore. We're not allowed to access the value because there is no value. It's been erased. All we're doing here is we're matching on type. Unit type, that's the base case. That means that we've got to the end of a tuple. So we just return an empty list. But the other case is the interesting one. We have a tuple with a head and a tail. So we're we're destructuring a tuple here using this special operator. So we're saying a tuple with a head element and some more elements. And that means that we can use this const value again to get hold of the actual string with that type. We have to tell the compiler that it's a string at this point, but we're sure that it is, so this is a safe cast. And then we recurse on the remainder of the tuple. So if you play that through in your head, you should see that we end up with a nice list. We'll end up with a list of strings, which is what we want. Next, for each field, we want to summon a show instance for the type of that field. So we have an integer field, a string field. What we want here is a list containing the show instance for int. Oops. Oh, sorry, strings for this. Show of string. Hello. And show of int. Then we'll iterate through the field values, and for each one we'll pick the corresponding show instance and use it to produce a string. So this summon all, this is another helper method which follows exactly the same pattern as LM labels. So it should look reasonably familiar, but it's using this summon in line function to say summon an instance of show for that type, which would be string or int. Sorry, this is not Scala. Next, we need the values of the fields. Because we have a product mirror, we know that A must be a subtype of product, so we can safely cast this to product and then just iterate through the values in it. And finally, we have all the information we need, so we just need to zip things together. Here we're calling the show method for each of our fields, and we turn it all into a big string. So that's the product case. Next we have the sum case. So here we have a sum mirror, and we have the value that we want to show. Because we have a sum mirror, we're able to call this method called ordinal. So the way sum types work, if we go back to our enum employee, this is a sum type, has two cases, and these are numbered. So this will be the 0th case, this will be the first case. So this ordinal thing, oops, given some value A, it will tell you which case it corresponds to. Is this a grunt or is this a CEO? Is it a 0 or a 1? Then we need to pick the correct show instance for that case. So we iterate through the mirrored element types, which again is a tuple of the different types. So this would be a tuple of grunt and CEO. We iterate through that until we get to the right one. So starting at 0, we're trying to get to the odd index of the tuple. We loop through it until we get to the right one. So if n equals odd, so we're at the right index of the tuple, then we are interested in this type T, say grunt, for example. Then because of the way ADTs work in Scala and elsewhere, we know that because we're in a sum type, each case of the sum must be a product type. You can't have a sum of a sum. It doesn't really make sense. So we know that it's a product. So we can summon a product mirror for that type T. And that means that we can delegate our showing to the show product function that we've already written. And if n is not equal to odd, then it means that we're still looping through the tuple. So we call ourselves recursively on the remainder of the tuple, and we increment n. If we get to the end of the tuple, then something's gone horribly wrong. This shouldn't happen. We just return an empty string. Keep that. Okay. So if we try to compile this, it should fail because it can't find a show of string because we haven't defined one. So if we provide just handwritten instances for primitive types like int and string, then we now have working show instances. So person looks as we'd expect. Pet looks similar, and you can see that it's for the nested person field, it's using the show instance for person. It's summoning it correctly. And grunt, or employee rather, is working correctly, and it's handling the fact that it's a recursive data type just fine. There's no infinite looping or stack overflows or anything. With that, I am out of time, I think, so I might have to give it a miss, the remainder. Oh, there's a question. Could you explain what erased value is good for and how it works? So erased value. So erased value is good for matching on types. The point of it here is that we don't have any value. So we can't just do a normal match. Normally you would do like to match case sum x. 0, something like that. Where you make use of the value on the left-hand side over in the right-hand side. But here, there is no value. All we have is type t. So we're kind of cheating or pretending that there's a value, but it's been erased so that we can match on type t. All we're interested in is the stuff on the right-hand side of the colon here, whether it's a unit or a tuple. So it kind of feels like a slight hack to me, just so that they could reuse the match and case syntax. I feel like there could be a nicer way to do this. There's also a feature called match types in Scala 3, which seems similar. I haven't really looked at them in detail, but it would be interesting to see how those overlap with this. I forgot to talk about inline. So when you do things like erased value of t, this kind of stuff only makes sense at compile time. So you have to do it inline. You need this inline keyword. That means that, well, it firstly means that your code will be inlined. So the body of this function summon all will be inlined into the call site. But also it means that you have access to this compile time only functionality like erased value. So if you write this kind of code in Dotty, then you have to get used to the word inline showing up all over the place. As soon as you inline in one place, you'll find that whoever calls that probably needs to be inlined as well, and then their caller needs to be inlined. So it kind of spreads out.
Cool. Thank you very much, Chris. I have a ton of questions as well. I don't want to take up too much time though, so I'll limit it down to one. So how did the recursive derivation actually work? Because I would have expected an infinite loop, or at least a kind of failure, because a show instance doesn't exist yet, right?
Yeah. So the first time I wrote this, I ended up with it hanging at runtime, which is not what I expected at all. And that was to do with a lazy val calling itself during its own initialization, apparently. That's a bug in Dotty. So I think the trick to this is that the match, or the entry point to the whole thing, happens inside the def of show. So if you were to instead do like match here, this kind of stuff, and each of these right-hand sides produced an actual show instance, show of A, and I think that would hang because it would keep trying to call itself over and over again. But because you're inside def of show, you kind of deferred the summoning of the recursive summoning of itself until after you're already inside the implementation of show. I think that's the trick, if that makes sense.
Yeah, that does. Gosh, that's an interesting way of thinking about it, though. My next question, though, I won't actually let you answer it because you don't have time, was going to be on how this would handle type parameters. But that's something I can go and research myself, I think.
You mean like a show of A of something?
Yes. And
yes.
Would it be
so
possible?
That's what my Functor example would have been all about. And the answer is it's really complicated because just the mechanics of this mirror stuff is not really designed for that, or not set up very well for that. So you have to do all kinds of tricks, like clever type aliases and things, to convince the compiler that you want a polymorphic type, not a plain old normal type. So if you have a look at the Functor code, it'll give you a hint. There's stuff called polymirror, I think. Oh, I could quickly give you a quick peek at it.
It's okay. I'll just share the code in the chat for anybody who missed it. Type class derivation in Scala 3.
Actually, this polymirror type stuff to say I want a mirror of a higher kinded type. And I want my mirrored LM types to be higher kinded as well. So you run into this kind of problem. And I was completely stuck on this, but then I found some code that Miles wrote for his Shapeless 3 branch, where he'd done this, and he saved me.
He always pioneers in that, I guess.
Yeah.
Okay, well, thank you very much. I thought that was really interesting. It was really cool to see the comparison between all the different languages as well in the beginning, and now how the plumbing works of it in Scala 3. This isn't something I
just quickly point out that there are a few more slides. So if you want to look at the final example with the macros, then I would probably have a quick look through these slides first, and then look at the code. It might make a bit more sense. Sorry, I couldn't get to it.
Do you have a link to the slides as well?
I do. I'll stick it in the chat in a second.
Okay. Thank you very much. Okay. Well, thank you. I think let's have a quick break of